Hi, everybody. So up to this point, we've been talking about kinematics, which is the study of motion. It's just a description of what's happening. We haven't really talked about why things are happening the way they are. Well, we're going to start that today. One of the first things that you're going to run into is the concept of inertia. Now, you may have some definitions in your mind from, high school or just from daily life about what inertia is. But really, inertia is indistinguishable from mass. There's no difference between inertia and mass. So something that has more mass, takes more oomph to get it going. Once it's going, you may say, oh, well, it's got a lot of inertia, and so it's hard for me to stop it from moving. Or equivalently, you might say, well, it's sitting there and it's got a lot of mass, a lot of inertia, so it takes a lot of oomph to get that thing going. But the reality is there is no experiment you can do that can distinguish inertia from mass. So while we're going to talk about mass, and maybe sometimes we'll even throw out that term inertia, you need to keep in mind that they actually mean the same thing. So what we want to introduce today is the concept of momentum. And up to this point, we've been talking about how much oomph you have. And really, we are talking about momentum. Now, you may have heard Newton's laws, maybe in high school or something like that, where you heard F equals ma, the force equals the mass times the acceleration. That's a lie. Newton never actually said that. All of Newton's laws are actually defined in terms of momentum because Newton realized that it's not just how fast something is going, it's also how much mass it's got, how much inertia it's got. So it takes both of those quantities to define how much oomph it has. Newton called this a quantity of motion. So that's actually where the term momentum comes from. So what we're going to do today is we're going to look at deriving a definition, a mathematical definition for momentum, and then we're going to talk about how we can use that to actually predict what's going to happen with a body. So if I have two things in particular colliding, what are going to be their final velocities when all of this comes out? Let's get started. All right, so take a look in your books here and looking at microtask 1. Anytime that we're going to try to create an equation, we're going to have to figure out what it depends upon and whether those variables are going to be indirectly or inversely proportional or directly proportional. Directly proportional means as this one goes up, the quantity I'm interested in goes up. And anytime we have something directly proportional, we're going to put that in the numerator of our equation that we work out. Now, remember, this is also directly proportional. If this quantity goes down, then the quantity I'm interested in goes down as well. The other type of relationship that we're going to run into is inversely proportional. So what that means is as this quantity goes up, the quantity that I'm interested in goes down. And the same thing could be the other way, of course. As this quantity goes down, the quantity I'm interested in goes up. When we're creating our equation, then anything that is inversely proportional goes in the denominator. So by taking all of these different physical quantities, these different variables, and putting them together, whether they're inversely proportional, directly proportional, that's how we get our equations. Now, I will caution you, and we'll talk about this in a minute, we cannot use this technique to figure out the constant that might be in there. We can only do that by experiment or by theory, as we've done in some of the other things. And so we'll see how that goes in just a minute. So take a look at your notes down here. We know that this momentum, this quantity of motion, depends upon the mass of the object and how fast it's moving, its velocity. So let's think about this. And I want you to pause the video and then make a choice. It's important that you commit to that choice, even if it's not the right one. Okay, how hard an object, that's our quantity of momentum, hits the wall, is it directly proportional or is it inversely proportional to the robot's mass? So for example, as the mass goes up, does it hit harder? Or as the mass goes up, does it hit less hard? Pause the video, think about that. Well, that one's pretty obvious, right? If I've got this big massive thing coming at you, it's going to hit harder. I mean, think about, which would you rather get hit with, a bowling ball or a ping pong ball moving at the same speed? Well, that bowling ball is going to hurt a whole lot more. So when we look at this, then we know that those are directly proportional. All right, now the next one we talked about is velocity. So if something's moving faster, will that cause it to hit harder? Or will it cause it to hit less hard, right? So is it directly proportional or inversely proportional? Pause the video and think about it, see what you get. Okay, so now we can think about this the same thing. Let's suppose that I have two pool balls, and they're the same size, they're the same mass, and I'm going to throw them at you. One of them I'm going to throw pretty slow, and the other one I'm going to use my patented 90-mile-an-hour fastball, and I'm going to throw that sucker at you. Which one is going to hurt more? Well, probably that fast one. So as the velocity goes up, then we know the momentum, the oomph, goes up, how hard it hits. So that one is going to be directly proportional as well. All right, so now take a look at the next page, and let's see if we can start putting these things together. So directly proportional, let me write this a little bit bigger so that you can see this. We know that it must be, the mass, for example, must be in the numerator. However, if I want to use this term, this symbol equals, it may not be exactly equal to the mass. In fact, it almost certainly isn't. So I have to multiply by some constant here. Now, this symbol, you may have seen this little fish symbols. This means is proportional to. So that means literally the momentum is directly proportional in this case to the mass. Okay, but just because they're proportional doesn't mean that they're equal. So instead, let's go ahead and erase this part. Good. Instead, what we're going to do is we're going to put this constant in here. Now, we can determine, as I said, we can determine this by experiment. We can do a whole bunch of masses and measure how much momentum they get. Or I can do this by theory. I can say, okay, well, this equation comes from this, and therefore the calculus says that constant have to be 1/2 or whatever it is. But at this point, we don't know what it is. Now, the other equation that we know, the other relationship we know, is that the momentum is also proportional to the velocity. So as the velocity goes up, the momentum goes up. And so we also need this constant here, this called a constant of proportionality. These two are not necessarily the same. In fact, they almost certainly aren't in most cases. But then the total momentum depends upon both of these factors. Right? Now, these two are just constants. They're numbers. Maybe they have units, maybe they don't. But these two are just numbers. So I could combine those into a single constant just, to make my life a little bit easier, right? So now at this point, all we can do is do experiments. And if you do the experiments like Newton did, you're going to find that C3, this constant, is just 1. And so my equation then is going to look like this. Now we're not quite finished. Is velocity a vector or is it a scalar? Well, it's a vector. So we need to indicate that that quantity is a vector here. However, remember what we said, that if I have a vector on this side, I need to have a vector on this side. So this must also be a vector. So that tells me that the momentum has both a direction and a magnitude. And if you think about it, that kind of makes sense, right? If I'm hitting something head on, that might hit harder than something that's maybe going off at some angle in there. Okay. All right. So this then is going to be our mathematical definition for the momentum. Now, you should be preparing your flip book for the exam, and I'm not going to give you too many more examples of this, but you might have a card called momentum. Now we haven't made any assumptions with this, have we? So this definition can apply pretty much anywhere. So we're going to have this. So my velocity then we see is directly proportional to the momentum, and my mass is also directly proportional to my momentum. Now, what we're going to do is we have to define every single term. So we know that this is the momentum, and we also need its units. Now here we've got something a little bit more tricky. So take a look at microtest 2, and we want to see if we can figure out what these units are. I'm not going to change the page just yet because we're going to lose what we're working on here. So let's get rid of this part up here. There we go. Give us a little bit of room. Remember that anytime we want to figure out the units of a quantity, all we need is any equation that involves that quantity. Doesn't even have to be a definition. Any equation that uses it, and from that we can get the units. So, well, here's an equation. So what are the units of mass? Well, the units of mass, of course, are the kilogram. What are the units of velocity? Those are going to be meters per second. So the unit of momentum is a kilogram meters per second. Now notice that I've got this little dashed line here. That does not mean subtract. Units are always either multiplied or divided. You will never add or subtract a unit while you're working out these fundamental units here. So that's just tradition. I mean, you will also see this written as this way, and sometimes you'll see it written as that, but now it starts to get a little less clear as to whether what that word actually is there. This, however, is the most common way to write it, is with that dash. But don't get confused and don't think that that means subtract the mass. It doesn't. It means multiply the mass. And if you look at our equation, you can see that's exactly what we've done. We've got our kilogram and times our meters per second here. All right, so then, as we said, this m is our mass in kilograms, and v is my velocity in meters per second, just like that. All right. Okay, so look at the next page, and I'm going to go ahead and advance through these two. Here, just to finish things up here, if you're going to fill that in, that's going to be kilogram meters per second. And mass is, of course, a scalar. Velocity is a vector, and so as we said, the momentum must also be a vector. All right, so let's look at a scenario. So as we get through this process, I'm going to be giving you less and less verbiage, less and less hints about what's going on with this. We're just going to give you step 1, step 2, step 3, step 4, step 5. You must be using this step for everything you do. Now you may say, oh, but Dr. K, this is really easy. I don't need to do this. And that's true. But remember, we want to teach the method using the easy things. We don't want to teach the methods using the really complex ones where you really do have to use the method for this. So humor me. Make sure that you're doing it using this method every single time, and trust me, it will pay off in the end. Trust me. All right, so here we've got two BattleBots, and they've been designed as sumo bots. So in the lab, often we'll play a sumo bot game where you've got a ring and you've got the two bots, and they have to find each other and push the other bot out of the ring. So we're going to have a collision here. Now, one of the things that we need to think about is, okay, what happens in a collision? Now, let's assume that there's no friction, everything's on a level playing field, this sort of thing. So what Newton found was that the quantity of motion of the system, both robots together, must be conserved. All right, so let's take a look at this, and we'll talk about what we mean by conserved in just a minute. But it wants to know what is the initial momentum of each robot. Okay, so our scenario then is simply find the initial momentum of two robots. And we're going to add those up to get our system momentum, or our total momentum. All right, well, we need a diagram here. So we'll draw a ground here, and maybe we'll get fancy and we'll put our red robot here. And remember, we want everything that's in our problem statement to be in our picture, so that I don't have to refer back to the problem statement, because you're more likely to pick up the wrong number by referring back to the problem statement than you are simply by looking at the picture. So we know that the mass of the red robot, so we're going to call that MR, is 1.5 kilograms. Always make sure you've got your units, because that can throw you off. We also know that its velocity, and I'm going to leave this as a vector, as a scalar, right? So this is V, R, and that's going to be 0.25 meters per second. But I don't yet know if it's positive or negative, do I? Let's see if we can clean up that V just a little bit there. So I need to know, is this in the positive direction or is it in the negative direction? Now you may say, oh, well, I'm just going to make this way be positive. And that's fine. We'll do that. But what we're going to see is there are very good reasons to make the positive direction be to the left in this case. All right. But just because that's probably the one that occurred to you first, we're going to set our coordinate system so that this direction is positive. All right. So now our blue, so that means that our red robot then, is it moving in the positive direction or in the negative direction? Well, it's moving in the positive direction, so we're going to put a plus right there. All right, now our blue robot then it says is moving directly towards the red robot. So it's going this way. We'll go ahead and extend our ground so he's not just, whoops, so he's not just hanging out there. All right, so we know that the blue robot, which we'll call MB, has a mass of 2.0 kilograms, and it's got a velocity going towards the red robot. So that's going to be VB, which is a vector, and it's got a velocity of 0.5 meters per second, 0.50 meters per second. But that's the magnitude. We need a direction. So is the blue robot moving in the positive direction or the negative direction? It's going in the negative direction. So we're going to put a negative sign right there. Okay. So there's my picture, and I've got all of the information that I was given in there. The only thing I don't have in my picture is, what are you looking for? Well, I want to know the total momentum. I want to know the momentum of each robot. So I want to know P red, and I don't know what that is, but it's in kilograms meters per second, and that is a vector. And I also want to know what is, we'll write it out here, PB, the momentum of the blue robot, and that's also in kilogram meters per second. My total momentum then is just going to be the sum of that. That's going to be my system momentum. So if you want to remind yourself of that, you could say, okay, momentum total is just equal to the red momentum plus the blue momentum, and that should be pretty straightforward. Okay. All right, so now when we're looking at our step 2, right now this one's pretty simple, right? We have a mathematical definition for the momentum. We have the mass and the velocity of each one. So maybe our step 2 will be plug in mass and velocity for each robot into momentum definition. And notice how I'm using the symbols to represent the words, and that's a good shortcut for you. All right, so step 3 then, we need to record all of the symbols that are here and their English meanings. Okay, so let's just go through over here. We know that MR is the mass of the red robot, and we know that that is going to be 1.5 kilograms. Now I'm actually going to do something a little bit different here. We did define the symbol first, that's fine, but I find it easier to write the words first and say mass of robot, mass of red, equals my symbol that's defined, MR. The reason for that is now I have MR equals 1.5 kilograms. And if I don't know what it's going to be, like I do up here, I would have PR equals double question mark. So either one is correct, and it doesn't matter. But I find that it's usually easier for me to write down these words here first. All right, well, we also want to use ditto marks as much as possible because we're lazy. So the mass of blue, and we define that symbol to be MB, and that's 2.0 kilograms. We define the velocity of red, and we call that VR. Remember, it's a vector. And looking at our notes, then we decided that was positive 0.25 kilograms. Notice that the problem didn't tell you a direction. There's no way for us to know what the direction is until you establish your coordinate system. That's another reason for having everything in your picture, because now we're going to know what our directions are. So our velocity of blue then is going, we decided that was going to be VB, and we decided, looking it up at our notes here, that was negative 0.50. Whoops, that would not be kilograms, would it? I hope not for velocity. That would be meters per second, and that would be meters per second. There we go. Now, the only other thing then are unknowns, and so we're going to say the momentum of red equals PR, and we don't know what that is, so we use double question marks, but we do know it's kilogram meters per second. And then the momentum of blue, and that's PB. And I don't know what that is either. Okay, so you should have all of this in your step 3. Now, if the problem had explicitly asked for the total, which we're going to talk about in a minute, then you probably want to put your P tot in there. But right now, it just wants to know the individual momentum of each robot. So that's going to be PR and PB. Okay, look over your step 3. Make sure you've got all that before we move on to the next step. All All right, so step 4 is the equations. And if you remember from step 3, we had 2 double question marks. So I need to have the same number of equations as I have double question marks. Okay, in this case, it's very easy. We're going to go through our flip book. We're going to look at that shell, that P equals MV. Remember, that's a shell. You're never going to write that down on your paper. Instead, you're always going to substitute in the symbols that goes with it. So just, writing the top part of our flip book here, we know that momentum, and then we had P equals MV, right? And then all the rest of the data down here. So this is my shell. I don't want to use this because I would end up writing the same equation twice. Or you might say, oh, I know it's for both of them. I'm just going to write it once. You now cannot be sure if you can solve the problem yet. And we're going to see why that's important here in just a very short period of time. All right, so our equations then, our symbol is P red, and that's M red, V red. And then our second equation then is PB, and that's MB, VB. So now you see, very simple, I have 2 double question marks, 2 unknowns, and 2 equations. Now I know the physics is done. I can relax. I have no more physics I need to do. All I need to do is now just do the algebra and put it all together. All right, so let's do that. I'm going to get rid of this over here just to give myself a little room. All right, now we went 1 page more than I wanted to, but that's okay. Let's go ahead and work it out. So with our step 5, then we started off, look back at your notes, we started off with PB equal, or sorry, we did red first, so we can do the red first, equals MRVR. Well, I don't have to do any rearranging for that, do I? It's already set up. This is just straight definition. So that's going to be 1.5 kilograms times, look back at your symbol list. You don't even have to look at the picture now, it's at the symbol list. And we saw that this was positive 0.25 meters per second. Now I have PB, and that was 2.0 kilograms, and it was negative 0.50 meters per second. Now, before we actually do the math, let's see if we can start building our physical intuition. When I had these 2 robots, I have a great big blue robot and a really small red robot. Now they haven't collided yet. They're separate robots. It's obvious they're going to collide, right? Because they're headed towards each other, but they haven't yet done that. After they collide, if they stuck together, just to make things simple, if they stuck together, would that combined mass, would it move to the left or would it move to the right? In other words, would it move in the negative direction or would it move in the positive direction? Stop the video and think about that. We really need to build this intuition of what's going on. Well, the blue robot is not only heavier, it's moving faster. Yes, it's negative, but that's a direction, so it's moving faster to the left. So you would predict then that the combined object would be moving towards the left in the negative direction. What that means is that my total momentum should be negative. Let's see if that's true. Okay, so we put this in to our notes here, and if you punch that in your calculator, make sure you pause the video and do that yourself, and we get 0.375 kilogram meters per second. And when we do this one, we get negative 1.00 kilogram meters per second. All right? And that makes sense. Our red robot is moving to the right. It's moving in the positive direction. So that means its momentum, its quantity of motion, must also be moving to the right in the positive direction. Same thing with PB, our blue robot. Its motion is going to be in the negative direction. So its momentum had better be in the negative direction. Now let's stop and get P total. Get that P total. Let's see if we got the same thing. So remember that we said that this is just the sum of the 2. So this is kind of a separate problem here. So all I need to do is add these up, and I get that P tot is going to equal negative 1.0 plus 0.375, which, if I'm doing my math right, is going to be negative 0.625. Make sure that works. Negative 0.625 kilogram meters per second. Is the total momentum of the system in the positive direction or the negative direction? It's in the negative direction. So And that makes sense. That's what you projected. That's what you predicted, right? When these things collide, it's going to keep moving in that direction. So our math here is justifying that. The important thing here is we're going to talk about the total momentum. So the total momentum is conserved. The total momentum doesn't change. That's what we mean by conserved. So let's erase this part, give ourselves some room. And unfortunately, I don't have the big giant eraser that I can get rid of all this at once, but that's okay. We're just going to clear out enough so that we can work. So when something is conserved, we say that it doesn't change. Well, how would we write that mathematically? What symbol do we use to represent change in? You remember? Well, that's that delta. That delta means change in. So in words, we say that the momentum, the change in if the change in momentum must be what? It must be 0 if it doesn't change. If the momentum is the same before and after, then it must not change. So it's equal to 0. Now there's 3 other ways that we could write, or 3 total ways that we could write this. So we know that this means change in. So that means that the final minus the initial must equal 0, right? That would be our change. And then I could also move this pi to the other side. And the momentum after is going to be equal to the momentum before. All 3 of those are mathematical ways of saying the English phrase, the momentum is conserved. By conserved, we mean it doesn't change. Now, we got to think about that a little bit, though. Can the momentum of the individual robots change? Well, think about our little red robot, right? It started out going in the positive direction, and it ended up going in the negative direction, probably. So certainly that robot's momentum was not the same before and after. And the same, of course, is going to be true with the blue robot. So individual momenta is the plural of momentum, individual momenta can change, but the total momentum, the momentum of the system, will not change. So we're going to add a little subscript here for tot. So our total then, I'm going to be a little bit lazy and erase these. There we go. Doesn't want to change the pen. There we go. So my total momentum after minus my total initial momentum must equal 0. And therefore the final total momentum must equal my total initial momentum. So again, really important, the individual momenta of the robots is going to change. Very often will change. However, the total momentum of the system, adding both of those together, will be the same before and after. So this kind of format where I've got the change in some number, some quantity equals 0, that is shorthand for this quantity is conserved. And so we're going to run into a number of quantities that are conserved. And in this case, it's the momentum, but you're going to see they could be other things as well. Okay, so given this then, let's start with this last form that we have, and let's look at microtest 3. All right, so let's start with our third definition that we gave for the conservation. And I'm going to put the initial term over here and then the final term over here. Now, remember that only the total system momentum is conserved. So we could write that as P total I equals P total F. Now, as an aside here, you will sometimes see people write something that looks like this. This little Greek capital letter sigma here, that means the sum of. So we've got maybe n equals whatever it is, 1 to 2 in this case, and then they would have n and n. So where they're just kind of looping through and adding them all up. They mean the same thing, and I find that writing total is actually a little more transparent in understanding what's going on. So that's what we'll do, but you should be aware that you're going to see this form sometimes when you're in your engineering career with this. All right. So now what we're going to do is we're working on microtest 3 here. Now what we're going to do is we're going to substitute in are expressions for the momentum for each one of these. So I'm going to write this as m1 initial, and then the vector v1 initial plus m2 initial and the vector v2 initial. So since we're starting out with two robots in this case, and then do the other side, and that just means m1 final v1 final must equal, or whoops, that should be plus, plus m2 final v2 final. Now, another notation that you might see sometimes is they want to show that this applies to any number of robots or objects that we may have going in there. And so I will put it up here, but on the, for example, on the left-hand side, you might see something like m1 I v1 I plus m2 I v2 I plus dot 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 plus mni vni, and then that equals the same thing on the other side. That just means, hey, we may have more than one, we may have more than two, we may have n, where n is some integer from here. I'm going to assume that you can actually extend this to say, okay, yes, I may have in my flipbook this expression right here, but I know that if I have three things, well, then I've got an m3i, m3, v3i, and so on and so on. So this equation here, along with our other equations, and I'll go ahead and relist them here. Let's go back to my eraser. Oops, the eraser doesn't want to erase for me today. There we go. So all of these expressions mean the same thing. So pen doesn't want to cooperate. Let's see if we can click on it manually. There we go. So our delta P tote is equal to 0. Our P final, or P tote final, I'll just write over that, P tote final equals P initial final. That was the form that we have down here. And we had P tote final minus P tote initial is equal to 0. This, and this all mean the same thing. They're all saying that momentum is conserved. And physically, the best way I think to think about it is the total system momentum before must equal the total system momentum after. That saves a lot of going through all this mathematical issues and things like that. Traditionally, this is how we write, hey, this quantity is conserved. But functionally, this is what we're going to use to actually solve problems with it. So I suggest that you have a flipbook page. You can either add it to your momentum page or have a separate page for conservation of momentum, so that you've got all these forms, but then, you know, make sure that you're saying, hey, yeah, this is the one I'm going to use pretty much all the time. All right. So let's look at a scenario then, so that we can see what's going to happen. All right, so in this scenario, we want to find the velocity of Team Red's robot, so the red robot, after the collision. So again, let's draw our diagram. We won't get fancy with the colors this time, but this is going to be a two-phase problem. I've got before the collision, I've got my two robots, and they're headed this way. And so they've got a mass, and we decided that the red mass was going to be 1.5 kilograms. And we decided that the blue mass was going to be 2.0 kilograms. And then they have an initial velocity. So V red I is going to be positive, if I set this way to be my positive, is going to be positive 0.25 meters per second, while the blue I is going to equal negative 0.50 meters per second. And those numbers just came from the previous scenario. We're doing the same situation. It's just now we found it before collision, now we want to find it after collision. So the second phase of my problem, which I'll draw over here just to give myself some room, is now they have collided, but I don't know which direction they're going after that, right? The math doesn't actually tell me. Now, my mass before my MRI is equal to my MRF. It's the same. So I can just get away with using MR. Now, but what about my velocities? Well, we predicted that the whole thing is going to, the total momentum is going to be going in the negative direction. And remember, I don't have a choice. This still has to be the positive direction. And we proved that by finding the total momentum of the system was actually negative. Now, even if they don't stick together, the total momentum of the system still has to be negative after the collision because it was negative before the collision. So what that means then is, if you think about it, as a system, these two robots have to be moving to the left. This first one is so massive that it's probably still going to keep moving to the left. You can't imagine that it's going to bounce off and go back, right? So we predict then that VB final is going to be in that opposite direction, but we don't know what its value is. Now, the red robot could, after collision, it can't keep on going straight, right? It's either got to stick together or it's got to bounce off. Well, since we know that the total momentum is going to be negative, we know that the red robot's final velocity is also going to be this way. But we don't know what it is, and that's what we're trying to find. Okay? All right, so our design then, anytime you have a collision, you want to think about conservation of momentum. Now, we're going to see that there are some times when conservation of momentum doesn't work, but in many, many, many cases, conservation of momentum is going to allow you to get that final velocities to determine what happened after the collision. So, since we have a collision, we're in our step 2, we're going to say we're going to use conservation of momentum. We're going to plug in our initial values, and we're going to solve for the final values. So that's kind of our plan. That's an end. Final values. Okay. So step 3 then would be to write down all our symbols. Most of the symbols are going to be exactly the same as we had before. So we've got the mass of red, and that's going to be MR, and that's going to be 1.5 kilograms. Mass of blue is MB, and that equals 2.0 kilograms. The initial velocity, that's the only thing that's really different here, is because we need to distinguish between our two phases. So I've got my initial velocity of red, which we call VRI, and we said that that was positive 0.25 meters per second. My initial velocity of blue then is going to be VBI, which is going to equal negative, that's a B, negative 0.50 meters per second. And then my unknown that I'll just put down here on the bottom, it says it wants to find VRF, and we don't know what that is. Okay, so and that's going to be in meters per second. All right, so the next step, which is on your next page, I'm not going to move forward so that we can have all of this here, but just flip your page and you're going to see step 4. And what we're going to do then for step 4 then is we just do our equations. So we'll write that right here. This is step 4. Well, we look at our design and we know that we've already planned to use conservation of momentum. So you go through your flipbook because your brain said, hey, you know, I think I'm going to use conservation of momentum for this, but you don't memorize the equations. You go through the flipbook and then you say, okay, I need to use my full conservation of momentum equation, but it's a shell. I'm going to fill in with the symbols that I've defined. So for example, it's just going to be MR. It's not going to be MRI, it's not going to be MRF because the mass didn't change at all. But now I'll have VRI plus, and again, this is just MB because the mass doesn't change. It's not MBI, it's not MBF. VBI, and that equals my final, which is MR, again, doesn't change. VRF plus MBVBF. Okay. So the next thing, we always do this, and this is why we're using that 5-step procedure. We always look at this and we say, okay, did I add any new symbols? Take a look. Did you add any new symbols? Well, sure, you added that VBF. So we're going to put this down here in our symbol list, VBF, and we don't know what that is. Well, now we need to have two equations to match our two double question marks, our two unknowns, but we don't have anything else. This is an alert to say, hey, this problem cannot be solved. There's no point in going forward with it. Literally, the problem cannot be solved. And whereas maybe in some of your earlier classes or in high school, the problem always had a solution, right? It was like a word problem. You were given the data and you plugged it into an equation and then that gave you an answer. That's not going to be the case anymore. When you get out in the real world, what you're setting up is telling you what additional information you need to have your team go find. And so here, if we want to have the final velocity of red, somehow we've got to have our final velocity of blue. So you go back to your team and say, hey, boss can't do this. There's no way to solve this problem. However, if you add a sensor to the blue robot that's going to give me my final velocity, then I can give you what you want. So before we get out there and we design this whole experiment and we sit down to do it and we go, oh, wait, and you look like an idiot, you're going to plan it out like this so that you know exactly what you need to do. Okay, so we find that if you look on the next page, then we decided, whoops, we've got a problem. We're going to need some kind of final velocity. And so if you look down in the paragraph, it says Team Blue measured that final velocity after collision to be 0.25 meters per second in its same direction that it was traveling before. Well, that makes sense, right? We knew that it should be still going this way, going to the left. But now we know that VBF is going to equal negative 0.25 meters per second. All right. So let's see if that makes sense. Originally, the robot was moving 0.50 meters per second to the left in the negative direction. It hit, and it's still going in the negative direction, but it slowed down. Does that seem reasonable? Well, sure, right? What I did was I basically transferred some of the momentum over to that smaller robot, that lighter robot, so that now it's also going to the negative direction. Well, that had to come from somewhere, and it came from my big robot. So if you think about it, it went like this. Okay. Well, now we've got everything that we need because this is no longer an unknown. We'll risk using my eraser here, and hopefully we can get back. So we now know that this is negative 0.25 meters per second. Okay, so all I need to do now then, I've got one equation, one unknown, I am good to go. So this is step 5. We're just going to take this equation, we're going to solve it. Normally you would rewrite that, but since it's right here above it, I'm not going to do that. So we want this VRF by itself, so we get MR VRI plus MB VBI minus MB VBF is equal to MR VRF. The next thing we need to do is divide by this MR. Now, here's something I see a lot of students do. They draw a big line underneath this and just put the whole MR underneath that. Never, ever do that. You need to divide by each term individually, not over the whole thing, or you'll never be able to simplify the equation and see what physically is going on. So let's divide each term by MR. Not the whole thing. So now we can see that that one cancels and that one cancels as it should. Let's go ahead and rewrite each step at a time. So this is VRI plus this ratio of MB over MR. And I won't factor it out yet, but we're going to in just a second. Minus MB over MR, VBF, and that equals what I'm actually looking for, which is VRF. All right, so now you see that I've got this ratio, this MB over MR term in both of these, so I can factor that out. And so I get VRI, or let's see, that should be plus the ratio MB over MR times VBI minus VBF, and that equals VRF. If you get this far on the exam, you are doing very well. Now all you need to do is plug in some numbers and you're going to get an answer. However, before we do that, let's look at the physical reality of what this equation is saying. Suppose I don't have a blue robot. Suppose we can simulate that by saying, okay, mb equals 0. So if mb equals 0, this whole middle term right here goes away. And I'm left with VRI equals VRF. Does that make sense? Well, sure, it didn't collide into anything, so it's just going to keep on going at a constant velocity. We don't have any accelerations or anything like that. This also tells us something interesting about the ratio here. The greater mb is, the greater this fraction is, right? Now, here my VB minus, it's VBI minus VBF, which is opposite from what you might be used to seeing. You might be used to thinking, oh, right, a change in is going to be VBF minus VBI, but that's not the case here. If you hadn't gone step by step, you might very well make a sign error here. So if I have, let's say, some starting velocity, we said that it was this in meters per second, and then I do minus another negative, right? I'm going to be adding to that. So I know that this is going to be decreasing, because I've got a negative number minus a negative number gives me a positive, right? So I'm going to be less negative if we say it that way. I could actually figure out, based on this, what is the minimum initial velocity I would need to be able to make this red robot turn around and go the other direction, right? If my MR is very, very high, so let's say MR is the big robot and MB is the small robot, then notice that this fraction here, this ratio, is going to be really small. If MR is the big bot and MB is the small bot, that fraction is going to be small. So we wouldn't expect it to have a whole lot of effect on VR, on the red robot, right? Because we've got this tiny little bug on the windshield effect. On the other hand, if MB is the bigger bot, as it was here, now that ratio gets to be very big. And so that number then, which is negative, this second term is always going to be negative, then that actually will cause VR to move in the other direction if it's high enough. So we get some interesting description of what's happening here. This equation is not just some math problem. It's a physical description of what's happening out in the real world. In the real world, you're almost never going to be able to simply observe the thing. If you've got a spacecraft, you don't have a camera pointed back at you. You have instruments that are giving you data. And so the equation is taking that data and telling you physically what's happening with the spacecraft, for example, so that we know what it's actually doing, even though I can't see it. So this is a really, really important technique. All right. Okay, let's look at one other. Okay, so we saw in the previous problem that I was short one piece of information. I needed to know the final velocity of blue in order to have the right number of equations and unknowns so that I could find the final velocity of red. But there's another situation where we don't actually need that extra sensor. Let's suppose that my robots do stick together. So rather than bouncing off, let's say that they come together and they stick together and then they move as a unit. Okay, so how does that change our situation? So let's go to our scenario then, and we want to find the final velocity of red if the robots stick together. Okay, so we're going to have our diagram is going to be exactly the same for the initial part. So here's my robot. My red robot's coming forward this way, and my blue robot is coming this way. Now we could, if we wanted to, define our coordinate system so that positive is to the left, because that would get rid of a whole lot of negative signs, wouldn't it? And so that's actually why in this case, defining your positive to the left is actually a better choice. But just so that we can compare our results with our previous problem, we're going to go ahead and keep that coordinate system in the same direction. So we're going to assume that this way is positive. All right, and then we know that my MR, remember, was 1.5 kilograms. My MB was 2.0 kilograms. And then our initial velocities are going to stay the same as well. So VRI, remember, was positive now 0.25 meters per second, whereas VBI was negative 0.50 meters per second. All right. What's different here is the final phase. Remember, it's still a two-phase problem. I've got before I collide, and then I've got after I collide. And we have to treat those phases separately with this. So I'm going to go ahead and just draw my line here. Now, though, my robots are actually physically locked together. Okay. And I want to know, what is the final velocity of red? Well, we've decided that since my total momentum is negative, then now we know for sure this whole thing has to be going to the left. It has to be going in the negative direction because they're locked together, right? So we know that VRF must be in this direction, but I don't know what it is. Well, you may say, well, I still need VBF, right? So I've still got these two unknowns. Think about it. How is VRF related to VBF? How are the final velocities of the red and blue robots related? Well, they're stuck together, so they better be the same, right? So there's two ways you could do this. You could say, all right, I'm just going to have an equation in my step 4 where I explicitly state that VRF is equal to VBF. And so you see that will be my second equation then that I can use. And that's often one of the best ways to do this, so that you can say, okay, no, I'm explicitly saying, hey, person, whoever's reading this, I'm assuming that these two velocities are going to be the same, because they are. The alternative way would be to define a different symbol. And I'm going to go ahead and erase these two. Because they have to be moving at the same velocity, we could just define this to be VF and say that they're the same. So I've got this new object, this combined object that's moving to the left at velocity VF. Either way works, you're going to get exactly the same answer, so you do you. All right, so what I'm going to do here for my step 2 then is I'm going to use conservation of momentum. And I'm going to plug in initial values, and let's go ahead and use VF for the velocity of both robots. Do you see that? So instead of using this technique here, which is perfectly fine and is actually a good one, we're going to go with the probably less obvious one where my VF is going to be the same. Okay. Now you go on to your next page. I'm going to stay on this one so that we can keep our work here. And so when we look at step 4 then, which are my equations, we'll put that up here. So for step 4, we've still just got one equation. I've got MR, actually let's put it down a little bit since it's going to be a little bit longer. So let's put our step 4 right here. Just draw us a line here. So our step 4, then we know that MR, VRI, so our initial robot red and velocity times its mass plus MB, VBI, that must equal, now here's where it's a little bit different. We know that both robots are moving at the same velocity, so we'll use the VF for that. And then MB is also moving at the same velocity. Now, if you don't like that, because that does require you to kind of think ahead a little bit, if you don't like that, then that's fine. Go ahead and make this a VB or a VRF and a VBF, and then add in that equation that VRF is equal to VBF. Now you still have two equations and two unknowns, and you know that the problem can be solved. So you do you. You do the one that makes the most sense to you. I just got to choose one to work through it, and so this is the one that I'm going to choose for this. Okay, so we've got our equation. Then step 5, we would ordinarily rewrite that equation. As before, it's right here, so I'm not going to do it again. So I need to get VF by itself. Because VF is now in my step 3 symbol list, I'll just add that one thing. So velocity of red and blue equals VF, and I don't know what that is. So everything else is going to be the same. I'm going to rewrite step 3 for you, but you should as good practice. All right, so I need to get that VF by itself. So the first thing I need to do is I need to factor out that VF over there. So I've got MR VRI plus MB VBI, and then I'm going to factor out the VF. So I get MR plus MB times VF. Let's see if this makes sense. So initially I have two robots. That's my MRVRI and my MBVBI. Afterwards, I have a single new object. And what's the mass of that object? Well, the mass is just the sum of those two, exactly like we have right here. So MR plus MB is the mass of my new object. And then that new object is moving at this velocity, this final velocity VF. All right, so now I'm ready to divide everything through by MRB. And remember, we do that on each term as we do this. So I get MR. Actually, let's just put it underneath to save some space. So this is going to be MR plus MB, and this one's going to be MR plus MB, and this is going to be MR plus MB. Okay. So rewriting that then, I get MR VR plus MB VB, because now I'm going to add these fractions. And you may say, well, Dr. K, isn't that the same thing as just drawing this line over here? And in this case, it is. But you want to make sure that you're not losing information from that. So I'm just adding the fractions here is what I'm doing. So this fraction plus this fraction. And that then is going to be equal to VF. And there's my final answer. So now all you have to do is just plug in your numbers and you'll get that answer. So when you're working this out, I want you to go ahead and plug in the numbers on your own. When you do that, when I did this, I got that my VF was equal to negative 0.179 meters per second. It's in the negative direction. That makes sense, right? Because my total system momentum is in the negative direction before. So the total system momentum, which is now just one object, must also be in the negative direction. And so I'm getting what I expect here with this value. I'm getting this negative number. You go through, work it out. It's good practice. The math, yeah, you need to be able to do the math. It's getting to the math that's the most important part. It's understanding those physical concepts. All right, so we've taken the time to learn how conservation of momentum works. Now, I want to stress that conservation of momentum does not apply all the time. It applies in most cases. You may have heard, oh, well, it's conserved, so, well, you know, that's a universal law, and that's actually not the case. If you think about it, let's say I have two robots that collide, and then a piece of it goes off. Okay, well, you can say, yeah, I can track that third piece. I have a third object. And you say, okay, that works. However, what happens if they come in and they bend? That's going to actually slow down the robot, isn't it? So if they come in like this, even if they bounce off, they're going to bounce off at a slower velocity than they would have if they had just touched without any damage going on. So something else is happening because it looks like we've lost momentum. And according to conservation of momentum, that shouldn't happen. So what we are talking about here is we have a special case if I don't have any outside forces, anything that's actually affecting things, bending of robots or anything like that, then I know, okay, yeah, it's going to be conserved. And in many, many cases, that's going to be true. You're going to be able to figure that out. When it's not true is what we're going to look at next time when we introduce the concept of work and energy. We'll see you then.